All right, in this video, we're going to derive the C6v character table. And so the way that this is going to work is the first thing we need to do is identify all the symmetry operations in this point group. It can help if we have a molecule that to use to visualize. So this is a molecule with C6v symmetry. It's a pretty rare point group, but basically know what it's going to look like. It's going to look like some molecule with 6 atoms like in a hexagon and then coming to a point. So you can think of like ammonia C3v. But it's like a tripod coming down there. This we have 6 points coming down. This ends up being germanium, gallium bonded to this benzene, but the details there don't really matter. And so we always are going to have identity. That's one of our operations. I use the hat notation to show that we have, if we're talking about an operation and not a class, and then going through this central atom, right, going through the center, of course, we have our principal rotation axis. That's our C6. So we're going to have the C6 operation. We're going to be able to do, that's a 60-degree rotation. That's interconverting, one of these hydrogens to the next. And then we're going to be able to do the C6 2 times. It's a C3, C6 3 times, C2, and a C6 4 times. That's equivalent to C3 twice. And that's a 240-degree rotation. And then last, we have a 300-degree rotation. That's a C6 5 times. We don't have the C6 6 times. That's not a unique operation. That is the same thing as identity, right? That equals identity. So we don't have that one. Let's think about how to, okay, fine. Let's come up with our other operations. Of course, this is a V point group. So we're going to have mirror planes, right? And we're going to have 3 mirror planes that we call sigma V's. And these are V's. They're coincident. They're not H's because they contain the principal rotation axis. And they go, we define it for the CNV point groups as if they go through the atoms, they're V's. And then we also have mirror planes that are sigma D's. And so these bisect bonds. And so you can see these types of mirror planes are different, but we could call these sigma V prime, and sigma V double prime. And then we have sigma D and sigma D prime and sigma D double. And these, now we have to, so that's it. That's all we have. We don't have any other mirror planes or any other rotations. Now we have to take these operations, and we have 6 operations here, 5 different rotations and identity, and 6 mirror planes. So we have 12 operations. We have to take these 12 operations and split them up into classes, group them into classes. And so the way that this works is that your sigma V's are going to go together and your sigma D's are going to go together. You can see because these sigma V's, it's kind of arbitrary how you define one versus the other. If you have different axis systems, you could interconvert between these two. And you can see they all do something similar. So if we're to take a look at this mirror plane here, it's going to interconvert these 2 sets of atoms, but all these other atoms, including the central atom, are going to stay the same. And if we look at some other mirror plane, like this one, again, it's these 2 sets of atoms that are going to be interconverting. They're looking at each other in the mirror. For the sigma D's, so these 3 sigma D's, there's a different color here. These 3 sigma D's are going to go together. Sorry, 3 sigma V's are going to go together. And I dropped the hat notation here because now I'm talking about a class. For the sigma D's, you can see they behave quite differently. So if we look at this one, these atoms interconvert, and these atoms interconvert, and then these atoms interconvert. So all 6 of these periphery atoms interconvert. And by the way, the other atoms on the hexagons interconvert in analogous ways. I just didn't show them there. But we have these 3 black arrows here, and in this case, we only have 2 black arrows. So it's doing something different. But all the sigma Ds are similar in the sense that they have 3 sets of arrows. So if we look at this sigma D, or these atoms are interconverting, they look at each other in the mirror. These atoms across from them are interconverting, and so are these. So again, 3 sets of arrows. So these 3 sigma Ds are all doing similar things. So we group them into the same class. Identity is always going to be in a class by itself. So that's by itself. And then we have to think about the C6s in the various rotation. Well, a C6 and a C6v, those are going to be in the same class. And the reason for that is because there's some arbitrariness as to what direction you rotate, right? If you do a C6 this way 60 degrees or a C6 this way rotate 60 degrees, those are going to be the same. But if you do a C6v in this direction, we get the same thing as if we did a C6 in this direction. So depending on how you define your axis systems of which way you rotate, C6 and C6v are functionally doing the same thing, okay? And the rigorous definition for this, like in CN point groups without the mirror planes, these would actually be in separate classes. So if you see my video on C6, character table, I explain how these are in separate classes. That's sort of a more even rarer point group. And so it has to do with the fact that the mirror planes can interconvert the axis systems that make these 2 operations the same, okay, equivalent. And so we can do the same thing with the C3 and the C3 too. So those are going to be in separate classes. So we can write that as 2C3 class. Let me get our blue class here. We'd write as 2C6. And then we're going to have a C2 that's going to be in a class by itself, right? If we do C2, C2 is the only one that takes, this atom and goes to that atom, right? 180-degree rotation. All right. So now that we have our operations, we can draw sort of the bones of our character table. And how we do this is we put the point group in the top left corner, and then we write all of our classes. We have the identity class. We have 2 C6s. We usually start with our principal rotation axis first. And then we have our 2 C3s. And then we have our C2. At this point, where you put these doesn't really matter. And you can swap these columns in any way. It doesn't actually matter, but this is sort of the most standard way. And then we have our mirror planes, right? So our mirror planes where we had 3 sigma V's, vertical mirror planes, and we had 3 sigma D's. Just make that look a little nicer here. Sigma D's are dihedral or diagonal mirror planes. And then we know that one of our rules of the character tables, if you look at my character table rule video, states that you have to have equal number of columns as rows. So we're going to put, for our irreducible representations, we're just going to use gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, and gamma 6. Because we have 6 classes, we need our character table to be a square. And so we're going to have 6 irreducible representations. Later on, we're going to use Mulliken symbols to name these vectors, these irreducible representations. But at this point, we don't know what the vectors are because we're deriving the character table. And so all we have to do at this point is keep them as something generic. So we just use this gamma nomenclature. So the first thing at this point now is to assign 1s to the first representation, 1s across the board. This is what we call the totally symmetric representation, irreducible representation, and every character table always is going to have one of these totally symmetric ones where you have ones across the board. Now, what do? Well, we like to play with different functions, okay? And so I always test z first. Now, if you go through this, so let's draw our axis system here. Remember, our z-axis is always how we define our principal rotation axis. So when we're talking about doing these various C6 type rotations, that has to be defined as a z-axis. How we define the x and the y, that's up to us. Of course, x, y, and z have to be perpendicular to one another, but that doesn't really matter. So we're going to test a z function, and we're going to ask the question, what happens to a z function, a z vector, if we do all these different operations on it? So if we do identity, which is the first operation in the first class, on z, we get z. And there's a 1-by-1 matrix that explains this transformation. Take z to z, it just has the value 1. And then we take the trace, or the character of the matrix, this is why it's called character tables. It's just a sum across the diagonals. Well, it's only a 1-by-1 matrix, so we only have one unit. And that tells us what the character is. So we use the Greek letter chi, and that just means character of. The character of the identity operation is equal to 1. And then we just march right along, we go to the next class. The next class has a C6 or C6v, right? Those are the two operations in it. And we can choose either one of those. We're going to get the same result. And we think about what happens when we do a C6 on Z. And if we do a 60-degree rotation on Z along in this way, our vector is still going to be pointing up. So we're going to end up with the exact same logic here, where we get chi of C6 equals 1. And the same thing is going to happen with C3 and C2. So, those are also going to be, I'm not going to write it all out, but C3, these are just different rotations. But again, because we're rotating with Z, nothing happens. So what about the mirror planes now? Well, we have 3 different mirror planes, and we can choose however we want. So let's define our sigma v as going through our x, one of the sigma v's as going through our x. We can see this vector is in the mirror. Maybe I didn't draw that perfectly, but let me try again with a different color. We define one of our sigma v's as being in the x z plane, right? We know it has to be in the z plane because it bisects the central atom there. The point is that the vector z is in this mirror plane, so it doesn't change. So again, we're going to get chi, the character of sigma v, is equal to 1. And if we now look at a different mirror plane, which is the sigma d, I'm going to choose that's a 45 degrees shifted, right? They're 45 degrees shifted from one another, the sigma v's and the sigma d's. That could kind of come out towards us and be bisecting the x and the y, but it still contains the z vector. And so again, nothing happens here. So this is a very boring example, but we figured out how the d vector transforms, the z vector transforms. And it just transforms as a totally symmetric representation. So that's good to know, but it doesn't help us derive anything, right? It didn't help us derive any more irreducible representations. So, but it's nice just going through it first, because it sets, I wanted to set for you all this sort of idea of taking the trace of this matrix, right? This 1-by-1 matrix, taking the trace, the sum across the diagonals to get the character. Because what we're going to do next is we're going to be forced to actually have a 2-by-2 matrix. So it's going to be a little more interesting. So let's go through that. We're going to test now, we're just testing vectors here. So we're going to test the x vector. So I'm going to change our vector here and be an x vector. And when we do the identity of x, well, we get x. And now we go on to our next class. We can choose C6 operation or C6v. Those are both operations in the 2C6 class. We choose C6. And we need to know how to rotate this. We have to use the rotation trigonometry matrix, which is cosine 2 pi over your n value, or 6, or cosine of 60. It's another way of saying this if you want to be in degrees, cosine of 60 degrees. Negative sine 2 pi over 6, and positive sine 2 pi over 6 on this component, and negative positive cosine over 6 in this component. So basically what this tells you is that xy is going to transform like this, okay? So x is going to go to cosine 2 pi over 6 times x minus sine 2 pi over 6 times y, and y is going to go to sine 2 pi over 6 times x plus cosine 2 pi over 6 over y. And so this x vector is going to be rotated 60 degrees, and it's going to be somewhere like this, right? So I just showed it dash. So it moved from there to there. And you can see that to describe this vector, it's not solely as x, it's not solely as y, it's some linear combination of both x and y, described by this rotation matrix. Okay, and so what that tells us is that this indeed is our rotation matrix. I can actually simplify this, and I just like to think about it in terms of cosine pi over 3, right? 2 divided by 6 is 3. X times y, negative sine pi over 3, cosine pi over 3, and sine pi over 3. So now the trace of this matrix is going to get us our answer. So the trace of this matrix is the character, right? Sum across the diagonals, that gives us our character. The chi, the character of the C6 operation for the x and y functions, which are transforming together, is going to just be equal to 2 cosine pi over 3. And cosine pi over 3 is 1/2. So this equals 1, 2 times 1/2. And so for our x vector here, and I'm going to put it down here because I know what the standard way ends up being for putting this character table. Sorry, it should be a 1. It doesn't really matter, right? It's all arbitrary. Which one's gamma 1, which one's gamma 4, you're choosing that. But I just want it to match what I know the answer is in the end. So I know this value is going to be 1. What this also tells us now is x and y transform together, right? You can't describe it how x transforms without also incorporating y, and you can't describe how y transforms without also incorporating x. So we also have to have y here. Y goes to y, of course, with identity. So then if we write the matrix, the 2 by 2 matrix, for how x and y transform, well, we get the identity matrix, right? 1's across the diagonal, which takes xy to xy. And then we take the sum across the main diagonal there to get the character, and we get chi of identity equals 1 plus 1, which equals 2. So we can plug in a 2 here for gamma 5. Okay, so then what about the C3, right? And the C3, we're going to have a very similar thing. And just for the sake of time, I'm just going to write this as just the on-diagonal elements. That's all that matters, right? You can see we didn't need these off-diagonal elements. They didn't contribute to the trace of the matrix. But this is going to be, if we do talking about C3 versus C6, it's going to be 2 times more that we have to rotate. So it's going to be 2 pi over 3. 2 pi over 3 is 120 degrees. So if we think about our unit circle, we are going to be in the top left kind of corner of our quadrant of our unit circle. So the chi of C3 is 2 cosine 2 pi over 3, right? It's just cosine 2 over 3, 2 pi over 3 plus cosine 2 pi over 3. And cosine 2 pi over 3 is negative 1/2. But trying to get at, so 2 times negative 1/2 is negative 1. So this gives you a negative 1. For the C2, we know that that's the next one, right, up here. We could use this formula as well. That will work, but we can just visualize this. We're spinning 180 degrees. And so we are spinning backwards. behind ourselves, this x vector went to negative x, and similarly a y vector would spin to negative y. So that tells us we need negative 1s on the diagonal. And that gets us the matrix that takes xy into negative x and negative y. We take the sum across the diagonals to get the character chi of the matrix. And the character chi of C2 is then negative 1 plus negative 1, which is negative 2. And so we plug in a negative 2 here. Okay, and if we keep going here, now we are on to sigma v's. So let's think about for sigma v's. Let's erase some of this just for clarity. I'm going to erase my sigma d. I can redraw it, I suppose. Let's see, there we go. Good job erasing. So x vector. X vector, I want to draw an x vector. We have that in red, and a y vector. We have it in blue now. X vector, so let's think about sigma v. Sigma v, we know we have to have a 2 by 2 matrix that keeps these together because x and y transform together. But sigma v for x is in the mirror plane. How we define this one? We can choose any sigma v. We just chose this one and we define sigma v as being in this one sigma v. Remember, there's 3 sigma v's in the molecule, but we find it as being in this green mirror plane. So x is going to go to x then. It's in the mirror. Y, though, is going to go to negative y, right? Because it's looking at itself in the mirror. And so this ends up being 1, 0, 0, negative 1. And we take the trace of that matrix, the character of that matrix, and we get chi of sigma v equals 1 plus negative 1, which equals 0. And so here we have a 0. All right, now let's do the sigma d. So, oops, I actually can keep these arrows, that's fine. Let me erase this reflection. I'm going to erase the sigma v we had. And let's draw now a mirror plane in green, which is one of the sigma d's. And remember, the sigma d's came out at a diagonal like this. That's why that d in their name. So if you look at that, bisects x and y. So the x vector is actually going to look at itself and look at y in the mirror, and y is going to look at x. So that tells us that xy, we have some 2 by 2 matrix that takes xy to yx. That matrix is 1s on the off-diagonal components. And you take the character of that matrix, the chi, sigma d equals 0 plus 0 equals 0. And so we can write here that x comma y, they transform together as this way, okay? And so at this point, it helps to either test some other functions, or we can try to use principles that we know. We could use other quadratic functions. For example, like the different d orbital functions, we have xy, xz, x squared minus y squared, xy, and z squared. We could think about it that way. Or we can do a rotation vector. And let's do a rotation vector, because I think it's always good to do one of these rotation vectors just so you can see what a rotation vector is. It's useful in circular dichroism spectroscopy. Selection rules there. It's also rotation translation. So when you're calculating group theory for chemistry, the rotational modes and translational modes, and then you subtract them off to get the normal modes. You know, it's useful information to have. So I'm going to erase this and erase this vector, these vectors as well. And what the rotation vector is it's basically just a curved vector. And if we define it as, if we are talking about the z vector, it is just the vector that's wrapping around the z-axis. So there's our z, there's the z-axis, and rz is just wrapping around. And what we're going to be looking for is, does rz change directions when we walked through one operation each from the 6 classes of the C6v character table that we're deriving here. All right, so identity is the first one, right? And so when we do an identity to anything, we get back what we started with. So that's not very interesting. We're going to get RZ goes to RZ. We have a 1-by-1 matrix that describes this, and we take the trace of that matrix, and that gets us chi of identity for RZ is equal to 1. What about a C6? Well, a C6, if we define it as in the same direction as our rotation vector. So we're going to be taking some vector that looked like this, right, how I drew it, and now it's rotating 60 degrees, C6, and it looks like that. Well, these are still both RZs. They're still rotating in the same direction, and in this case, counterclockwise. So RZ still goes to RZ, and so you're going to get the same 1-by-1 matrix with a value of 1, and so chi of C6 is going to be equal to 1. So we have 1 and 1. We had 1 for identity and 1 there. And we're hoping that this generates something new. It has symmetry RZ. What about if we do C3? Well, if we start off with something like that, it's just going to rotate 120 degrees now, so it's going to rotate even more. But I think you can see it's still going counterclockwise. So chi of C3 is also equal to 1. And same thing with C2. Okay, it's going to do the same sort of thing, where it's just rotating in the same direction, so you get the same vector. Now, what about the sigmas? So what about sigma v? So let me go back and draw our sigma v. We defined it as being in the x plane, and I guess I should have drawn that a little taller so that we can see how it cuts through the z-axis. So what happened here? This arrowhead is in front of the mirror plane, so it's going to end up behind the mirror plane, right there. And this tail is behind the mirror plane, so it's going to end up in front of the mirror plane. Kind of imagine this is sort of the mirror plane there, how I drew it. And so now we get a clockwise arrow. And so this is going in the opposite direction of what we started with, right? It's opposite. So this is telling us that RZ goes to negative RZ. And of course, the 1-by-1 matrix that describes this transformation just contains -1. And we take the trace of that matrix, the sum across the diagonals, and we get -1. So chi of sigma v operation equals -1. Okay, and then what about with the sigma d? Well, sigma d is gonna actually, the exact same sort of logic is gonna happen. It's gonna cut through, it's a little hard to see here, but it's cutting through, it's cutting the rotation vector in half. So the same thing's gonna happen, where we get the swapping of the heads and the tails. So our chi sigma d is gonna be equal to -1. So that's kind of cool. And so we did indeed use this rotation vector to generate a new irreducible representation of 1, 1, 1, 1, -1, -1. And at this stage, it's always a good anytime you generate a new vector, it's a good chance to make sure you did it, to check it. It's a good time to check to make sure you did it correctly by checking to see if the new vector you generated is orthogonal, and it should be orthogonal with all the other vectors that you already have. That's one of our character table rules. Again, see my character table rule video on that, but we can check that. And so let's check gamma 1 dotted orthogonality is the dot product has to be equal to 0, but it's a dot product normalized or adjusted for the number of operations in each class. So how I'm going to write this is gamma 1 is 1, comma 1, comma 1, comma 1, comma 1, comma 1, right? And dotted with gamma 2, which is that we just got, which is 1, 1, 1. Okay. So that's all fine, but we have to then, like I said, adjust this dot product to take into account the number of operations in each class. So what that means mathematically is we need to multiply the number of operations in each class by one of the vectors. So there's one operation in the identity class, so we multiply by 1. There's 2 operations in the C6 class, so we multiply by 2. 2 operations in the C3 class, so we multiply by 2. 1 operation in the C2 class, so we multiply by 1. 3 operations in the 3 sigma v class, so we multiply by 3. And 3 operations in sigma d class, so we multiply by 3. And then we see if this is equal to 0. I'm just going to simplify this out. So undo our multiplications here. Carry this gamma 2 out, and then remember the definition of the dot product is you multiply each component. So the first component is 1 times 1, and then you add them. 2 times 1 plus 2 times 1 plus 1 times 1 plus 3 times -1 plus 3 times -1, and that all turns out to equal 0. First half here is +6, the second back end here is -6. So that equals 0. And so that's what you can do. You can check all of these. You know, it's a good idea to get a habit of doing this. Once you kind of understand the mechanics behind this, you can actually do it in your head. You don't have to, write this all out, and possibly you were able to do it in your head without me writing it all out. But I was just doing that for clarity. Okay. So at this point, we can really sort of puzzle the rest of this out is probably the next way to go. Oh, and one thing that we failed to do early on was usually when I have these, if you've looked at these other character table derivation videos that I have, after we put all ones across the board, we look at the sum of the squares of the dimensionality. So the sum of the squares under the identity class has to be equal to the order of the point group, which is the number of symmetry operations in the point group, which in this case is 12, right? 1 plus 2 plus 2 plus 1 plus 3 plus 3. That's one of our character table rules. Again, see the character table rule video. So we can actually get out these numbers here pretty easily. So we did this sort of later on. We could have done this early in the beginning, but it doesn't really matter. So we have some unknowns here. And what we know from this character table rule is that 1 squared plus 1 squared plus a squared, the sum of the squares under the dimensionality of this first column, plus b squared plus 2 squared plus c squared has to equal 1 plus 2 plus 2 plus 1 plus 3 plus 3, which equals 12. And that's just summing up all the operations here, right? 1, 2, 2, 1, 3, 3. Okay, so these values under the dimensionality, they can only be 1, 2, 3, 4, or 5. And 90% of the time, they're going to be just 1s or 2s. Only the higher symmetric, really high symmetry point groups like tetrahedral, octahedral, icosahedral, are these going to be 3, 4, or 5. Okay, and so you're looking for 2s and 1s. And if you work through this, right, you can see that, well, 1 squared plus 1 squared plus 1 squared plus 1 squared plus 2 squared plus 2 squared equals 12, right? Because we have 8 here and then 4 ones, 8 plus 4 is 12. So we can erase these ABCs, and that just helps us puzzle some of this out. Then I have another 2-type system. So we can choose whichever ones we want to puzzle out first, doesn't really matter. And the reason, when I use the word puzzle out, what I mean is basically use the orthogonality principle to help you, right? And so why was gamma 2 orthogonal to gamma 1? I always like to look at gamma 1, making it orthogonal. So I'm going to try to make something where I'm trying to come up with gamma 3, and I'm going to try to make orthogonal with gamma 1. Okay, choose something that's orthogonal with gamma 1. It's just simplest because it's ones across the board. And why was gamma 2? I want to just go over why gamma 2 very quickly. You can see why it's going to be orthogonal to gamma 1. Well, gamma 1's all ones, right? And then we have to normalize it for the number of operations in each class. So really we're dotting gamma 2 with the top number of operations in each class. And so we have 2 negative 1s here. That gives us a 6 overall, right? A negative 6. So we have negative 1s here. Negative 3 and a negative 3 when we multiply it out in dot product. And here we have 4 1s, but that's going to give us positive values, but it's going to give us a positive 1, a positive 2, positive 2, positive 1. 1 plus 2 plus 2 plus 1, that's a 6. So this component gave us the negative 6, right? When we were working through the dot product, that was the back half, I called it. And this is the front half. This gives you the positive 6. So you can get away with only having 2 negative 1s and having this balance it out because these were worth 3. So can we figure out some, and that's a natural thing. We have 12 operations overall, so we split it into 6 and 6. Is there some other way we can split this into 6 and 6? Well, what if we split it into 1, 2, and 3? So what if we do, we have our positive ones, maybe that's the first place to start here, easiest place to start here. Our positive ones, just our 1, 2, and 3. Well, now we're already worth positive 6, and so we know we need 3 negative. This is going to be 1, 3, and 3. Sorry, 1, 2, and 3. Made a mistake. That's fine. That's the nice thing about this. You can put in wrong values, and then if you're wrong, well, you just keep testing other values. So I'm looking for 1, 2, and 3. It says splitting up 3 and 3. That's a 6. And 1, 2, 2, 1. I want to do 1, 2, and 3. So I have 1, 2, right here, and then 3. And then I'm going to put negatives. 2, 1, and 3. 1, 2, and 3. That's going to be orthogonal, right? So we know that's orthogonal with gamma 1. And now we can test it with gamma 2. So this is going to be worth a 1. Gamma 2 dotted with gamma 3. I'm testing now. Does it equal 0? We have a 1 here. That's by 1. We have a 2 here. So 1 plus 2, we're at 3. Doing this in my head now. Negative 1, negative 2, we're at positive 1. Negative 1 here times 1, we're at 0. And then I got a positive, negative 1 times a 1. That's a negative 3. I'm at negative 3 overall. But then I'm negative 1 times negative 1, that gives me a positive. I'm at 3. So I'm good. And then I can test gamma 3 that I just derived with gamma 5. I got a 2 here. I got a 1, so I'm at 3. I got a 4. Sorry, we forgot to normalize the number of operations. I have a 2 here. I have a 2 here, so I'm at 4 because of this 2. Here I'm at 6, so this 2, and this became a positive 1. So I'm at positive 6. All these better be negative. And let's see what happens. Negative 2, negative 1. That gets me an 8. And so I'm in trouble because that is not going to be orthogonal. Let's see, let's just double check. 2, positive 2, positive 4, and here is 6. And then here we have an 8. So there's no way, and then we're going to have zeros here. There's no way this is going to work. So this didn't work. Okay? So that was actually wrong. It has to be orthogonal all the way through. Okay? So what other combination of 1s and -1s can help us out? Well, let's look at this gamma 5. Since it gave us trouble, let's try to see how this could maybe work out. Well, what if we put a +1 here, right? That seems nice because this -2 would cancel this +2. Now we have zeros here, but we know we have to, if we have a +1 here, we have a 1 and a 1. That's going to cause us some problems because remember we said when we're doing with gamma 1, we had to pair it as 1, 2s, and 3s. So we're not going to be able to pair it as 1, 2s, and 3s, but what if we paired it, can we pair it any other way? And we can't, right? If we put two 1s together, and then we can't get to 6 anyway. So this is going to actually have to be a -1, it appears. That brings us to +4 so far. And then if we want 1, 2s, and 3s, well, we could try putting a +1 here. It's just puzzling this out, guys. It takes some time. But I'm trying to walk you through the logic of how this works. It's a lot faster doing it this way than trying to find functions that work, because it's going to end up being, in this case, only some cubic functions that work, which get quite complicated. So right now, we're trying to make 1, 2, and 3. So that means one of these has to be positive. What I mean by 1, 2, and 3, 1, 2, and 3 are positives. So the other ones are going to be negative. That ensures me that I'm going to be orthogonal with gamma 1. Am I orthogonal with gamma 2? I got 2 plus 2 is 4. I got 6. This is okay. And then I got 8. And so again, I am not orthogonal. So I'm having. So what can we do? Well, let's see where did this go wrong, right? Where it went wrong, oops, sorry, was we had too much positive action here in the beginning, right? And so the reason why we had too much positive action is because we had a positive here and we had a positive here. So what if we flip these such that it's like that, right? And this is a +1. And what that did is we still had that 1, 2, 3 and 1, 2, 3 grouping with gamma 1 because both these were 2s, but now we're better aligned for gamma 5. So gamma 1 is still going to be orthogonal. And now gamma 5, we're going to get a 2. We're going to get, this is worth -2, so we're at 0, right? -1 times 2. Then this is -1 times 1. Testing, just for clarity here, gamma 3 dotted with gamma 5. We're hoping this equals 0. So 1 times 2 times 1 is 2. 2 times -1 times 1 is -2, so that's 0. 2 times 1 times -1, right, -2. 1 times -1 times -2 is +2, back at 0. And these have zeros in it, so we're good. This is equal to 0. And lastly, let's just test that gamma 2 is orthogonal to gamma 3. We force gamma 1 to be orthogonal by this 1, 2, 3 pairing, but you can double check it later if you want to. 1, -2, so that puts us at -1. +2 puts us at +1. -1 puts us at 0. -3 and +3. -1, -1, 3. -3 and +3 gets us 0. So we are good. We found a function that works. And so it seemed what worked well here was putting this -1 and 1. That was necessary for the gamma 5. And so I'm going to do the same thing, right? The same thing for gamma 4 now. Now we can't have two vectors that are the same, so that's wrong. But notice that these at the end were both zeros. So if they're both zeros, who cares if this is from an orthogonality point? Times it by 0 is going to go away. Who cares if these are both, if we write it this way, -1 first, or if we write the positive one first. So I'm just going to switch the order, swap the orders. And that turns out to be the right answer. Again, we're going to have, if we test, well, we kind of already know. Gamma 3 dotted with gamma 4 was orthogonal. So these are going to be orthogonal too, because we have multiplied by zeros. And then you can test the other ones, right? But we have this 1, 2, 3 pairing with the positives. 1, 2, I mean, that is a number symmetry operations, 3, and the negatives are 1, 2, and a 3. So that's going to be gamma 1, and it all works out. And then we can Sudoku out or puzzle out this last one, right? And so we need this to be different in some way. And so oftentimes in this business, it's good to just make a dramatic change first. So I'm going to put a 2 here instead of a -2. And what that's going to do is it's going to make this a positive component here. And so we're going to need some negatives here probably in the beginning that are worth 2 to straighten this out. So let's see. If we could do with the 1s across the board, that's easy to see. So this would be worth 4, positive 4, right? And then we have -2 and -2. So that was actually equal to positive. Sorry guys. So 2 times 1 is 2 plus -1 times 1 times 2 is -2 is 0. And then we have a -1 times 1 is 2, and 2 is 0. So if we put zeros here, then we're already at 0. So maintain it by putting zeros. And there's some symmetry here, right? We have the zeros here. So let's see if this works. So a good one to test, probably a complicated one, is gamma 5 dotted with gamma 6. 2 by 2, that's going to get 4. Maybe I'll write this down in a separate little color here. -1 times 1 times 2 is -2. -1 times 1 times 2 is +2, plus 2. 2 times -2 gives us -4. And then we have 0 times 0 and 0 times 0. And look at that, 4 minus 2 plus 2 minus 4 equals 0. So that works out. And let's just test some other ones just to make sure, but it looks like we're on the right track here. Gamma 2, but by gamma 6, 1 dotted with 1, 1, and 2. Got a 2, 2, 1, and -1. It's -2, 2, 1, and -1 is a -2, 1, 1, and 2 gives us +2, and then we have zeros. And so that all worked out. So gamma 2 is good. So we know gamma 2 dotted with gamma 1 is good, we know. Gamma 2 is good, we know. Gamma 5 is good. Let's try these 2 more, and then we'll be set. But usually once all these are working this long, all the other ones are going to fall into place. So you can be pretty sure that this is working at this point. We'll go through it. Let's do gamma 3. 1, 1, 2. It's kind of fun Sudoku. 2, -1, -1. So that gives me a +2. Multiply these numbers here, right? Dot product. 2, 1, and -1, -2, 1, -1, and 2, -2, and then I had zeros. So that also works. And our last one, let's test the gamma 4. It's amazing how this all works. Gamma 4 dotted with gamma 6. So that gives us 2. That gets us a 2. That gets us a -2. It gets us a -2, and then zeros. And again, 2 plus 2 minus 2 minus 2 plus 0. 0 is 0. So it all works out. And again, gamma 4 dotted with gamma 6 is equal to 0. All right. This stage, we got all of our vectors. And the only other thing to do at this point is to give the Mulliken symbols. And so the Mulliken symbols are There's rules for these Mulliken symbols. I have a video on that. But the Mulliken symbols, you give it an A or B if you're symmetric with if the dimensionality is 1. So if the character under E is 1, you're going to give it an A or a B. You give it an A if it's symmetric with respect to the principal rotation axis, the highest order n. So C6 is the highest number there, Cn, n equals 6. It's the highest number there. So it's symmetric, so we give it an A. Symmetric, we give it an A. It's anti-symmetric, -1, we give it a B. It's anti-symmetric, we give it a B. Now, how to distinguish between these two A's and these two B's? We normally look at the sigma V's. And so here are the sigma V's here. You can see like the Mulliken symbol rules use the sigma V's because they usually alternate. If we looked at C3s, it wouldn't help us, right? And even with the C2s, but the sigma V's do. So we'll get A1 if it's symmetric with sigma V, and a 2 subscript if it's anti-symmetric. B1 because we're symmetric, and B2 because we're anti-symmetric. And these are going to be E's. We call them E's because the dimensionality is 2. This E doesn't mean identity. How do we, distinguish between these two? Gets a little vague here, and usually just put 1 and 2 and make sure that what you're calling E1 and E2 are the same with what somebody else is calling E1 and E2. But those are just labels. It's just part of the language. It's not anything intrinsic to the math. But there it is. So I'll also have a video on deriving where some of the quadratic and cubic functions come up with. We did x, y, and z, and rz, but I'll do xz, xy, x squared minus y squared, and maybe one or two cubic functions. So that'll be in a separate video.